Hello everyone. This is the first of a series of videos dedicated to redox chemistry. We are going to be looking at performing calculations involving delta G, Gibbs free energy, K, the equilibrium constant, and E, which is electrode potential in standard conditions and in other conditions. We'll also be looking at how to predict the spontaneity of redox reactions. We're going to be looking at the Nernst equation and how to perform calculations which involve the use of the Nernst equation. And we would also be looking at various diagrams that allows us to make predictions and calculations on the results of redox behavior of different elements, specifically Frost-Epworth diagrams, Latimer diagrams, and Ellingham diagrams. So we are going to be looking at half cells and galvanic cells. As a reminder, a galvanic cell is one which is set up around a redox reaction which is spontaneous. So it produces electricity, which is a difference with an electrolytic cell. An electrolytic cell, an electrolysis processing, is one in which the redox reaction is not spontaneous. So it will consume electricity for the reaction to happen. The equation that describes the half cells, which is the reduction process and the oxidation process that together will make the redox process, which is the basis of any galvanic cell, it's always written by convention as a reduction process. So even if one of the reactions will be a reduction and the other one as an oxidation, they are always written as a reduction, and you will find those reactions in tables, always written as a reduction reaction. No chemical reaction happens in a half cell on its own. As hopefully you know, a reduction reaction does not happen on its own. An oxidation reaction does not happen on its own. There needs to be an exchange of electrons, so both need to happen at the same time. So one of the elements will exchange electrons with the other. When you combine those two half cells, that reduction and that oxidation, in an electrical circuit, the redox reaction will happen if there's a potential difference between those half cells, and that is when you will obtain a galvanic cell, a cell which will produce an electric current. The typical example of a galvanic cell is a Daniell cell. So in the left-hand side, you have the copper ions in solution, which are reduced to copper metal. On the right hand side, you've got the zinc metal, which is oxidized to zinc 2+. When we write this in a summarized form, we express it like this. We first put the oxidation process, and we specify the state of the metals or ions. These two lines mean a Sol bridge, so it's representing this part of the cell. And then on the right hand side, you have the reduction process. See, this is a standard way of presenting the information in a cell. We talk about the standard cell potentials, E supra 0 cell. And there is a relationship between the standard cell potential and delta G, the free energy. And this is the relationship. Delta G, the change in free energy, is minus Z, which is the number of moles of electrons transferred per mole of reaction, so the number of electrons exchanged. F, which is Faraday's constant, and the electrode potential of the cell. The electrode potential of the cell is given in volts, and the units of delta G is joules per mole. And the super 0, this little symbol here, means that we are performing this reaction under standard conditions. And what are those standard conditions in an electrochemical sense? Well, the unit of activity for each component in the cell is 1. Pressure for gases is 1 bar. Solids are in the standard state. The pH is 0. and the temperature is 25 degrees, 298 kelvins. So that is what we call a standard, those are the conditions for a standard electrode potential. Another useful electrode potential in biological systems is the biological standard electrode potential, in which all the conditions are the same except the pH. It's not zero anymore. For standard biological conditions, the reactions are given at pH 7. So on one hand, we have the relationship between the free Gibbs energy or free energy, the change in Gibbs energy, and the equilibrium constant for the reaction, and this is the known relationship. The change in Gibbs energy is equal to minus R, which is the equilibrium constant for ideal gases, T, the temperature in kelvins, times the log of K, the equilibrium constant for the reaction. And on the other hand, we have this other relationship. Delta G is equals to minus Z, F, electron potential of the cell, with Z being the number of moles of electrons exchanged and F Faraday's constant. So I'm going to ask you now to stop the video and, using those two equations, this one and this one, come up with one or two expressions which will relate K, the equilibrium constant, to E, the electrode potential in standard conditions for the cell. So stop the video now. I hope you stopped the video and had a go at the exercise. So how would I go about that? Well, on one hand, I've got that delta G super 0 equals minus R T log of the equilibrium constant. And on the other hand, I've got another expression for delta G, which is the one that relates delta G to the electrode potential in standard conditions of the cell. So if I equal those two expressions, then I have as a result something that will relate the electrode potential of the cell to the equilibrium constant of the cell. I change the signs and I rearrange the equation, and I can leave them in logarithmic form, and then, well, this is what I get. Or I can leave it in, if I elevate to the power of E, which is the inverse of ln, I get that K equals E to the power of all this. So these two expressions, which are the same way of writing the same relationship between K and the electrode potential for the cell, for a particular cell. So what would be the conditions for a thermodynamically favorable cell reactions? What would be the values for delta G and for the electrode potential of the cell? Well, thermodynamics tells us that for a reaction to be spontaneous, delta G has to be a negative number. So because of this sign here, that means that the electrode potential of the cell is going to be a positive number. So a positive number of the electrode potential will tell us that that reaction is spontaneous, because delta G for that reaction will be negative, which is the requirement for a spontaneous reaction to happen.